more in this section in the next one, which is basically related to the second derivative. And we're going to see how this connects to some of the other relationships we've seen so far between the first derivative and the original function. So on page 241, we should have filled out this little connection chart here. Some of you might not have it ready, so that's why I'm going to do it here. That way what we do today actually makes sense. So we're going to dive into the second derivative, which is basically the slope of the first derivative. Okay, how is the first derivative changing? And we also brought in a new vocabulary word called a point of inflection, and how that's kind of a key characteristic to identify. So for those of us that did view the video assignment, can you help us kind of fill this out for those of us that don't have it completed? If the second derivative is equal to 0 or undefined, okay, that's something else that's a little bit new, like if a derivative doesn't exist, can we think about how that relates to an original function or the first derivative? Go, Christian.
In the first derivative, it is a potential max or minimum, and then in the original function, it is a potential inflection point.
Okay. A PIP. Okay, so that's what I call it, a PIP for short, possible inflection point. So potential inflection point. Now, up to this point, we said that if the first derivative was 0 or undefined, that was a possible max and min for the original function. Okay, we did a bunch of that at the beginning of the year. But now notice how we're taking the same connection, but we're moving it to a different set of functions. Instead of working with original and first derivative, now we're working with second derivative and first derivative. Okay, so this connection between the second and the first derivative is the same connection that we've seen between original and the first derivative. It's just kind of moving up in a different set of functions. This one's new though, a potential inflection point, and an inflection point is where your concavity is changing. For instance, if I look at a cubic function, originally I'm concave down, but then I reach some point where I change concave up. So this is a point of inflection where the curvature changes, and that's what we're going to spend a lot of time with working on in this section. What if the second derivative is positive? What would that mean? Maybe we'll start here. What would that mean for the first derivative? Yeah? It's increasing. So if you want to think about it, if I were to take one prime mark away from the second derivative and one prime mark away from the first derivative, isn't this the same connection we've seen? First derivative positive means original function is increasing. Okay, so if I throw in a prime mark, it means the same thing, but for those two new functions, if that helps. All right, negative would mean that the derivative is decreasing. But how do these second derivative values relate back to the original function if this is dealing with concavity now? If the second derivative is positive, can we think about the curvature of the graph? Good, Christian?
Concave up.
Okay, for positive. And then what about negative?
Down.
Concave down. Okay, so in my example here, this is a concave down section where you look like an upside down parabola, and then the other piece would be concave up where you look like a regular parabola. We can also talk about the changes in sign, positive to negative. If we change positive to negative, this would mean the first derivative now has a max, and negative to positive would mean that the first derivative would have a min. But in terms of the original function, we're just going to say that it has a point of inflection. Okay, there's some location where the curvature is changing. It's not as specific as a max or a min, but it's just a location itself. All right, so I'm hoping that's kind of a good review from what we did over break. The responses from the Google Sheet, a lot of you were saying how you're still a little confused. You understand how this information for the second derivative relates to the first derivative because those are the same connections that we've been dealing with so far, but we still might be a little confused on how this is the way it is, like why these connections are true. So let me ask you this. Let's say I start, you don't have to write this down, I just want you to pay attention and kind of let it sink in a little bit. If this is an initial slope, maybe we'll say it's 1, okay? So we would say f prime is 1. If I let the slope stay 1, do I have any curvature? No. So notice how if the first derivative is not changing, it's not increasing, it's not decreasing, I don't have a point of inflection. Notice how we're not changing positive to negative or negative to positive. Okay, so there's no point of inflection in this case. Now, if I start with a first derivative of 1 and I want to increase the slope, maybe I'll have 2, 3, 4, something like that. This is the slope value. How would you describe that curvature of f of x? This is the original function. Isn't that concave up? Okay, so if the second derivative is positive, notice how the slopes are increasing, the steepness is getting greater, then you're creating a concave up shape. Very similarly, if I start with a slope of 1 and then I want to decrease, so I'll go a half, a third, a fourth, maybe 0, okay, flat. Isn't that a concave down shape? Okay, so that's where the second derivative is negative. Okay, the slopes are decreasing. So we originally were looking at where f of x is increasing or decreasing, but now we can take a look at where f prime is increasing or decreasing to check out the concavity. Is that a good visual? Can we let that sink in a little bit? Okay. So what we're going to do today is just kind of rapid fire here on the next page. Out of all of these combinations, we're going to try to relate what those connections are to a particular function, either original, first derivative, second derivative. You can use the chart to help you out, but we're going to try to see how far we can get with these relationships. So they're telling us that f of x is increasing. What can we conclude about the first derivative? Yeah.
It's positive.
Positive. If the slope is positive, the original function's going up, aka increasing. Number 2, very similar. If f of x is decreasing, then the first derivative, aka the slope of the tangent line, is negative. All right. What if f of x has a maximum or minimum, a high point or low point? How does that relate to the first derivative? Christian, you're on a roll, yeah?
Is it 0?
It could be, okay? So if I have a parabola shape, that's definitely 0. But if I have an absolute value, because notice how that's still a minimum, that's not 0 there. So this is an example where the first derivative would be 0 or undefined. Okay, but there's something definitely going on with the first derivative though. We'll say 0 or undefined, and something else has to happen, yeah?
Does it have to be continuous?
Yep.
Oh wait, differentiable.
Well, not necessarily differentiable, because this one's not differentiable here, but it still has a minimum. Okay, that would be the undefined part where the derivative doesn't exist. What has to happen to your slope if you want to create a low point or a high point? Changes. Okay, so changes sign, either positive or negative to positive. Okay, so your first derivative has to be 0 or undefined. Okay, that would give us these two options, either a smooth curve or a sharp point, but you also need a sign change to help you create that maximum or minimum. All right, f of x has a point of inflection. Okay, so the curvature is changing. How is that related to the first derivative? If you look at the chart that we just did, what do we think?
Is it a min or a max?
It's a min or a max. All right, that one was new. What about 5? If f of x is concave up, so we have the curvature of a regular parabola shape, what's our connection to the second derivative? Positive. All right. When we're relating all these different derivatives to an original function, the first derivative tells us slope, okay, where we're increasing, decreasing, or max or min. Second derivative tells us concavity, curvature, concave up, concave down, point of inflection. Okay, kind of just as a general connection there. If we're concave down, second derivative would be negative. All right, and then notice how 7 is the same as 4. Okay, f of x has a point of inflection, but now they're asking us for the connection to the second derivative instead of the first. So let's say we have another point of inflection though. What does that mean about the second derivative information? Yeah?
Is it a 0 or undefined and has a sign?
Yes. So it's very similar to this connection we had for number 3. Okay, so minimum and maximum comes from 0, undefined, and changes sign for the first derivative. If we're talking about concavity, aka a point of inflection somewhere, then we're going to have the same result, but with using the second derivative. Okay, so this is where it can get confusing because we have the same relationships, it just depends on which pair of functions we're working with. And it's just going to take us some time to get used to them. What if the first derivative is increasing? So the slopes are increasing. How does that relate to the second derivative?
Concave up.
Oh, if this was f of x, that'd be concave up, for sure. Positive. All right, so maybe that'll help. If you can determine concavity, concave up, you therefore know the second derivative would be positive. Okay, so you might have to do a little balancing back and forth, but it should still get you there. If the slopes are decreasing, that's going to create a concave down shape, which means the second derivative would be negative. All right. What if the first derivative has a max or min? Can we think about how that relates to the second derivative? Yeah?
0 or undefined.
Or-
Sign change?
There we go. Well, maybe not sign change, because maximum, minimum kind of implies a sign change. So 0 or undefined. Looks good. If the first derivative has a point of inflection, how does that relate to the second derivative? What do you think? Minimum or max? Good. All right. F prime changes negative to positive. The slopes are changing negative to positive. How does that relate to the original function? Good, Anush? Minimum. All right. The slopes change positive to negative. Connection to the original. Yeah. Maximum. The slopes, or the slope has a maximum or minimum. Connection to the original. Yeah?
There's a potential inflection point.
Point of inflection. Good. All right, second derivative changes positive to negative. So what does that mean about the first derivative? If you took a prime mark away from each of them, maybe that'll help. It's the same connection, just applied to a different set of functions. Can we think about it that way? If the first derivative changes positive to negative, that's a max. Okay? So if the second derivative changes positive to negative, that means the first derivative has a max. Okay? It's the same connection, just a different set. And then last one, second derivative changes negative to positive, that's going to be a min. Okay? I know it's a lot to take in, because we're just adding more connections to the ones that we previously had. But we're going to spend a lot of time looking at graphs and picking apart different characteristics to help us relate all of these relationships together. So what I need you to do, it might be a little difficult, but we're going to fill in this chart here, and on page 243 and 244 you have different graphs. And they told us what certain graphs are, like an original function, a first derivative function, or a second derivative. But we're going to try to figure out what are the other graphs. Okay, how are they related to each other? So it's kind of a matching game, but we have to think about it a little bit. So we'll do maybe 1, 2, 3 together, and then maybe I'll let you try 4 and 5 on your own, maybe tomorrow, depending on how much time we have. Okay, so we'll start with the first one. They're telling us number 9 is an original function. All right, so we're looking at number 9. What I want you to do on the top corner, if this is f of x, let's think about some connections to the first derivative and second derivative. That way we can kind of narrow down which ones they might be. So what are some things that you notice about this graph? Increasing, decreasing, max, mins, curvature, anything. What do you think, Christian? Yeah.
It is decreasing from negative infinity to looks like -1.
Yep.
Increasing from 1 to 0.
Yep.
Decreasing from 0 to 1.
Mm-hmm.
And then 1 to infinity is increasing.
Okay, so if that's where this function's increasing and decreasing, can we relate those intervals to either one of these derivatives, either the first or the second?
I think if, for the first derivative, if it is positive f of x, or not positive, if it's increasing, f prime of x is positive.
Positive. Okay, so we're positive where we're increasing. So negative 1 to 0, and you said 1 to infinity. And then we're negative from negative infinity to negative 1 and 0 to 1. So that must mean we're on the x-axis where we equal 0 at those changes from increasing to decreasing. So that would be our maxes and mins. So 0 at negative 1, 0, and positive 1. All right, so we'll eventually try to find a graph that fits those descriptions. So we need a graph that's above the x-axis, below the x-axis, and then has these x-intercepts. We'll tackle that in a little bit. What about the second derivative? So now we're going to look at curvature. Okay, can we determine where this original function is concave up and concave down, roughly? If you start to trace it, are we concave up or concave down? Up. Okay, so negative infinity to maybe we'll say negative a half. All right, somewhere right there. And then notice how I change because I have a little itty bitty section that's upside down. So that would be negative a half to maybe positive a half. And if I continue to trace, notice how I'm concave up again. So we'll say positive a half to infinity. All right, so if you're concave up, that means the second derivative has to be positive, meaning above the x-axis on its graph, and then negative down below. And then we are 0 at negative a half and positive a half, okay, where those changes happen. All right, so with that information, maybe we'll start with the first derivative. Can we find a graph that is above the x-axis on these intervals, below the x-axis on those intervals, and then on the x-axis at negative 1, 0, and 1? Might be on this page, might be on the back page, might have to do some flipping. You see, Griffin?
Number 12.
12, okay, so negative 1, 0, and 1 work out for the x-intercepts. We are above on that interval and that one, and then below afterwards. Looks good. All right, so on our chart, we'll label 12 as the first derivative graph. All right, so then we got to find another graph that has these characteristics. So we need to be above the x-axis on these intervals, below the x-axis on those intervals, and on the x-axis roughly at negative a half and positive a half. So can we find a graph that fits those descriptions, either on the front or the back? Yeah? Let's check out 3. Oh yeah, negative a half, positive a half roughly. We're above and we're below. Looks good. All right, so on our chart, we'll label 3. Okay. One other characteristic that might help us out is looking at the type of function we have. Notice how the original function is a W shape, so that would be quartic. If you take a derivative, then that graph would have to be cubic, okay, and that's definitely what 12 was. And if you take another derivative, the next one would have to be quadratic, right? And that's definitely what 3 was. So you can look for types of functions as well. Okay, and another helpful hint. All right, let's try the next one. So the next one, they're telling us 6 is the first derivative. All right, so we'll label this one f prime. Let's see what we can figure out about f of x and f prime of x. Let's see, this graph is cubic. So can we think about what f of x or f double prime should be? If we take a derivative, that would be quadratic. But if we go backwards, quartic, good. All right, let's pick apart some characteristics. So we're either going to analyze, if this is the first derivative, if we analyze the slope of this graph, that's telling us something about the f double prime. Okay, the slope means derivative, so another derivative there. And then if we, let's see, analyze maybe maxes and mins above and below x-axis, that can tell us something about f of x. So where do you want to go from there? We can focus on f of x or f double prime. Let's see. We have x-intercepts at -3, 0, and 1. So what does that tell us about f of x? If this is a derivative graph, what does that tell us about an original function?
It has mins or maxes.
Mins or maxes. Okay, so min slash max at -3, 0, and 1. We can get a little bit more specific, like analyze above or below x-axis to help us specifically max or min, but generally that's okay now. If the first derivative is positive, okay, meaning above the x-axis, what does that tell us about the original function? First derivative is positive. F of x is increasing. Okay, so f of x is increasing interval -3 to 0 and 1 to infinity. We could do the other intervals. That would be where f of x is decreasing, so -infinity to -3 and 0 to 1. Okay, I think that's enough for us to try to pick out a graph. Let's try the second derivative, okay, which is the slope of the first derivative. So if we analyze increasing and decreasing in this case, that's going to help us with this information here. So if we're increasing from -infinity to -2, and then roughly a half to infinity, notice how the slope would be positive. Okay, so that's where our slope, or in this case, second derivative, would be positive. And then decreasing, we'll say -2 to a half, so we're negative, and that means we're 0 at -2 and a half. All right, so maybe we'll try f of x first. Can we find a quartic graph, kind of like a W shape, that has maxes and mins at -3, 0, and 1, and is increasing and decreasing on these specific intervals? Might be on this page, might be on the other page. Can we find it? Yeah?
Is the original 15?
Yeah, right there. Good. Okay, so it's a very exaggerated W, but we have min, max, min, okay, at the appropriate spots. And it looks like we're increasing and decreasing in the right intervals. So we'll put down the original function as 15. All right, let's go back, and now we're going to try to find the second derivative graph. So quadratic, U-shape, above x-axis on these intervals, below x-axis on that one interval, and then x-intercepts at -2 and a half. Yeah? 14. -2 and a half. Looks good. How are we doing so far? it's going to take some time. Okay, I completely understand because we're adding a whole new layer of connections. Okay, because we're adding a whole new derivative. It's a second derivative. But we're going to stop there for today, and then we'll go ahead and try the other three tomorrow.
See the same on both.
Steve, you gotta answer.